What if I told you that in 1963, a boat engine embarrassed every carefully built hot rod at the drag strip? Not a race engine, not some exotic European power plant, a boat engine from Buick. Dan, and picture this. It's a Saturday night at Lyons Drag Strip in Long Beach, California. The air is thick with nitro fumes and testosterone. A primer gray 32 Ford Roadster rolls up to the line. The announcer can barely contain his laughter as he reads the specs over the PA system. In the right lane, folks, we have Tommy Ivo's 4-engine dragster, 450 cubic inches of blown Chrysler Hemi power, and in the left lane, he pauses, squinting at his notes. A Buick nailhead with marine cooling? Nay, the crowd snickers. The flagman shrugs. The tree drops to green. 7.8 seconds later, the Buick-powered Ford is sitting in the winner's circle, while Ivo's crew is picking up pieces of connecting rod from the track's surface. The boat engine had just run the quarter-mile faster than machines built specifically for that 8-second blast of violence. And it wasn't even breathing hard. This is the story of how Buick's Marine Division accidentally created the most unlikely hot rod hero of the 1960s. An engine designed to push 40-foot cruisers through choppy water for 8 hours straight that ended up dominating drag strips from Pomona to Detroit. An engine so overbuilt, so understressed in automotive applications, that it made traditional hot rod builders question everything they thought they knew about going fast. But here's where it gets interesting. To understand why a boat engine could humiliate purpose-built race motors, we need to travel back to 1953. General Motors is riding high. Chevrolet has the small block V8 in development. Cadillac is selling luxury faster than they can build it. And Buick? Buick is about to make a decision that would accidentally revolutionize both marine propulsion and hot rodding. The marine engine business in the early 1950s was dominated by two companies, Chris-Craft and Gray Marine. Both were building engines based on pre-war designs. Flathead 6s mostly, some straight 8s. Reliable? Sure. Exciting? About as exciting as watching paint dry on a humid day. These engines made their power at 2,800 RPM and topped out at 3,200 if you were brave. They were agricultural in nature. Boat anchors, literally and figuratively, Nan Buick's chief engineer, Charles Chain, saw an opportunity. The company had just developed their new V8 architecture, internally called the front nail head, for its small valve diameter relative to bore size. The valves looked like nail heads sitting in the combustion chamber. While this limited high RPM breathing, it created something special, massive torque at low engine speeds. The engine made peak torque at just 2,400 RPM. That's tractor territory. But Chain realized this characteristic, seen as a limitation for automobiles, was perfect for marine applications. One-run boats are different from cars, fundamentally different. A car accelerates through gears, letting the engine spin up to its power band. A boat is always in top gear, always fighting maximum resistance. From the moment you advance the throttle, that propeller is trying to move thousands of pounds of water. There's no clutch to slip, no transmission to multiply torque. Just raw grunt from idle to redline. The standard 322 cubic inch nailhead made 188 horsepower at 4,000 RPM in automotive trim. Decent for 1953, but nothing special. The torque figure was more impressive, 300 pound-feet at that low 2,400 RPM peak, but marine applications presented a unique challenge. An engine in a boat runs at wide-open throttle for hours, not seconds like a drag race, not minutes like a road race, hours, sometimes entire days. Lechner and Chain assigned a team of 6 engineers to what they called Project Marina. Their mission: adapt the nailhead for marine use without compromising its reliability. The team was led by Joe Turley, a former Packard engineer who'd worked on that company's marine engines before joining Buick. Turley understood boats, More importantly, he understood what killed boat engines. And heat was enemy number one. A car engine at highway cruise might use 30% of its rated power. A boat engine at cruise uses 70 to 80%. Constantly, the cooling system in a car has airflow to help. A boat engine sits in a closed engine compartment with no airflow, surrounded by humidity that makes cooling even harder. The team's solution was elegantly overbuilt, and first, they increased the water jacket capacity by 40%. This meant casting new blocks with thicker walls and larger coolant passages. The automotive block weighed 195 pounds. The marine version tipped the scales at 268 pounds. That's 73 pounds of additional iron, mostly for cooling capacity. And the cylinder heads received similar treatment: larger water passages around the exhaust valves, additional coolant crossovers between cylinders. The automotive heads weighed 38 pounds each. Marine heads, 52 pounds. The extra mass acted as a heat sink, absorbing temperature spikes and dissipating them slowly. But the real innovation was the cooling system itself. Instead of a traditional radiator, marine engines use raw water cooling. Lake water, ocean water, whatever the boat is floating in, gets pumped directly through the engine. This presents a corrosion nightmare. Salt water can eat through cast iron in months, if not properly managed. Turley's team developed a closed cooling system where raw water cooled a separate freshwater circuit, similar to how a radiator works, but using a heat exchanger instead. This kept corrosive water away from internal engine parts while providing superior cooling capacity. The water pump was completely redesigned. The automotive unit flowed 90 gallons per minute. The marine pump, 240 gallons per minute. At full throttle, the entire cooling system volume was exchanged every 3 seconds. The pump impeller was bronze instead of steel, resistant to corrosion and cavitation. The housing was doubled in thickness. Now, here's the kicker. The oiling system got similar treatment. Marine engines experience different G-forces than automotive applications. A boat can slam into waves, go airborne, land hard. The oil needs to stay put. Turley's team designed a dual pickup oil pump with a 7-quart capacity sump. The automotive engine held 5 quarts. The pump itself was a dual-gear design flowing 40% more volume than stock. Oil pressure at idle was 45 psi. At operating RPM, 75 psi. Most automotive engines of the era ran 30 psi at cruise.ds. The internals were where things got serious. The crankshaft was forged steel instead of cast iron, not just any forged steel, but SAE 50 chromium alloy steel heat-treated to a Rockwell hardness of 3842. The automotive crank was good for 5,500 RPM occasionally. The marine unit was tested to 7,000 RPM continuously, though it would never see those speeds in service. The main bearing journals were increased from 2.5 inches to 2.625 inches. The rod journals went from 2.25 to 2.375 inches. Larger journals meant more bearing surface, which meant better load distribution. And the connecting rods were the real overachievement. Forged SAE 4340 steel with a tensile strength of 145,000 psi. The automotive rods were rated for 95,000 psi. The marine rods were shot-peened after machining, a process that bombards the surface with small steel shot to create compressive stress that resists crack formation. Each rod was magna-fluxed for cracks, then balanced to within 1 gram. The automotive tolerance was 5 grams. On-end pistons were forged aluminum instead of cast. The compression ratio was lowered from 8.51 to 7.2.1. Lower compression meant lower peak cylinder pressures, less stress, more detonation resistance. Remember, boats often ran on whatever fuel was available at remote marinas. Quality was inconsistent. The engine needed to survive on 67-octane swamp gas if necessary. The camshaft was probably the most interesting deviation. Where the automotive cam was designed for good street manners and reasonable fuel economy, the marine cam was all about one thing, making torque below 3,000 RPM. The intake duration was shortened from 256 degrees to 244 degrees. The exhaust duration went from 262 to 248 degrees. Less duration meant less overlap, which meant better low-speed cylinder filling. The lobe separation angle was widened from 108 degrees to 114 degrees. Wider separation meant smoother idle, important when you're trolling for fish at 600 RPM for hours. N-exhaust N-valve springs were another area of overkill. The automotive springs had a seat pressure of 65 pounds and 180 pounds open. Marine springs, 90 pounds seated, 220 pounds open. Higher spring pressure meant better valve control, but more importantly, it prevented valve float if the engine encountered violent motion from wave impacts. The springs were made from chrome silicon steel with a shot-peened finish. Each spring was tested to 1 million cycles without loss of pressure. The cylinder heads themselves were extensively modified beyond just cooling passages. The combustion chambers were fully machined instead of as cast. This ensured uniform compression across all cylinders. The valve seats were hardened steelite instead of plain iron. Stellite is a cobalt chromium alloy that maintains hardness at high temperatures. It's what they used in jet engine turbine blades. Absolute overkill for a boat engine running 3,500 RPM, but it meant the valve seats would last essentially forever. The intake and exhaust valves were upgraded to 21 4N stainless steel with chrome stems. The automotive valves were plain carbon steel. Stainless resisted corrosion from moisture-laden air and exhaust gases. The valve faces were given a 30-degree back cut to improve flow at low lift. Remember, with the mild cam, the valves never opened very far. Every bit of flow improvement at low lift translated to better cylinder filling. Nen. So, what was actually going wrong with regular hot rod engines that these boat motors solved? Then traditional hot rodding in the late 1950s and early 1960s followed a formula. Take a small block Chevy or Ford, bore it 30 thousandths over. Install high compression pistons, maybe 11.1 or 12.1. Add a radical cam with lots of duration and overlap. Port and polish the heads. Multiple carburetors, headers. The result was an engine that made impressive peak power, usually between 5,500 and 6,500 RPM. But below 3,000 RPM, these engines were doggy. They'd barely idle. They'd foul plugs in traffic. And when you did hammer them, you better make your run count because something was going to break. The boat engine philosophy was completely opposite. Maximum durability at moderate speeds with huge torque. When hot rodders discovered these characteristics translated perfectly to street and strip applications, it changed everything. The first documented case of a marine Buick in a hot rod was Mickey Thompson's 1958 dragster. Thompson was looking for reliability over outright power. He'd broken 3 Chrysler Hemis in a month, connecting rods, mostly. His crew chief, Fritz Voigt, suggested trying a Buick Marine engine he'd seen at a boat shop in Long Beach. Thompson thought he was joking. Voigt wasn't. When they bought a complete 364 cubic inch marine engine from Peninsula Marine for $800. That's about $8,000 in today's money. Expensive, but cheaper than rebuilding Hemis every weekend. The engine came with everything: the closed cooling system, the massive oil pan, even the 2-inch exhaust manifolds designed for marine use. Thompson's team stripped the marine cooling system, installed an automotive water pump and radiator, and bolted on a GMC 671 supercharger. The combination was unusual. Superchargers typically work best with high compression engines. The Buick's 7.2.1 compression was considered way too low. But that's exactly what made it perfect. The low compression meant they could run massive boost without detonation. Where most blown engines ran 6 to 8 pounds of boost, Thompson's team cranked it to 15 pounds, then 18, then 22, then in 22 pounds of boost. The math gets interesting. Atmospheric pressure is 14.7 psi at sea level. Adding 22 pounds means the engine was seeing 36.7 psi absolute pressure. That's 2.5 times atmospheric pressure. The engine was effectively displacing 910 cubic inches worth of air and fuel. The forged internals just laughed at the cylinder pressures that would have scattered a traditional hot rod engine. Mas the first pass was a revelation. Thompson's previous best with the Hemi was 151 miles per hour in 9.2 seconds. The Buick, 158 miles per hour in 8.9 seconds. But here's the beautiful part. The engine was barely stressed. Oil pressure stayed rock solid at 70 psi. Water temperature never exceeded 180 degrees. The plugs came out looking perfect, a nice tan color indicating ideal mixture. Thompson ran 28 passes that day. The engine never missed a beat. Known in word spread quickly through the racing community. If Mickey Thompson was running a boat engine, there had to be something to it. Within 6 months, Buick Marine engines were back-ordered nationwide. Peninsula Marine went from selling 5 engines a month to 5 a day. They couldn't keep up with demand. But the real genius of these engines wasn't discovered until road racers got hold of them. Drag racing is 8 to 10 seconds of violence. Road racing is hours of sustained high RPM operation. Sound familiar? It's exactly what the Marine engines were designed for. Dan Gurney was the first to campaign a Buick-powered sports car in SCCA competition. His 1959 Chevrolet Corvette Special started life with a 283 small block, making 290 horsepower. Reliable enough for sprint races, but in endurance events it would overheat or drop valve seats. Gurney's mechanic, Wayne Leary, suggested the Buick Marine engine after seeing Thompson's success, and on the engine they chose was the 401 cubic inch version, the largest nailhead Buick offered in Marine trim. Stock, it made 242 horsepower at 4,000 RPM. That's less than the Chevy, but torque was 410 pound-feet at 2,400 RPM. The Chevy made 290 pound-feet at 3,800 RPM. The Buick had 40% more torque at 1,600 fewer RPM, and Leary performed minimal modifications. A Carter AFB 4-barrel carburetor replaced the Marine 2-barrel. Tube headers replaced the cast manifolds. A lightened flywheel improved throttle response. That's it. No porting, no polishing, no radical cam. The engine made 275 horsepower at 4,200 RPM and 435 pound-feet at 2,600 RPM. The first race was Riverside International Raceway's 6-hour endurance event. 122 laps of the challenging 3.275-mile circuit. Temperatures that day hit 104 degrees Fahrenheit. Track temperature was measured at 138 degrees. These were engine-killing conditions. And by the third hour, half the field had retired with mechanical failures, mostly overheating, some thrown rods, a few seized pistons. Gurney's Buick, running 180-degree water temperature and 65 psi oil pressure, exactly where it started. The massive cooling capacity and overbuilt internals were finally being used as intended, just on asphalt instead of water. Dan Gurney won by 4 laps. The second-place Ferrari had to make 2 stops for coolant. The third-place Jaguar dropped a valve. The Buick never missed a beat. After the race, Leary pulled the valve covers to inspect. The valve train looked like it had just been assembled. No wear marks, no discoloration from heat. Nothing. And think about that for a second. An engine designed to push a 15,000-pound boat through water just won a sports car race against purpose-built racing engines, not through sophisticated technology, not through exotic materials, through sheer overbuilding and understanding of thermal dynamics. The Marine Buick's success caused a revolution in hot rod building philosophy. Instead of radical cams and high compression, builders started focusing on durability and torque. The phrase "end run what you brungry" became "hust run what won't break." Reliability was the new horsepower. By 1962, there were an estimated 3,000 Buick Marine engines in hot rods nationwide. Dealers couldn't keep them in stock. Peninsula Marine opened 3 new facilities just to handle automotive customers. They even created a Hiron Street Marinage package that deleted the heat exchanger and raw water pump, saving buyers $200. The factory got involved in 1963. Buick's performance division, seeing the success of their marine engines in competition, created the Super Wildcat 465. This was essentially a Marine 425 with automotive accessories. Forged crank, forged rods, forged pistons, but with higher compression and a more aggressive cam. It was marketed specifically to drag racers with the tagline, "Oz built like a boat engine, runs like a scalded cat." The 465 made 3 to 60 horsepower at 4,400 RPM and 470 pound-feet at 2,800 RPM. These numbers might not sound impressive today, but remember, this was 1963. A 427 Corvette made 430 horsepower, but needed 6,000 RPM to do it. The Buick made 85% of that power at 73% of the engine speed, and it would do it all day long. On. The engineering philosophy behind these engines influenced Detroit for decades. The idea that overbuilding for one application could create advantages in another became standard practice. GM's later big blocks, the 454 and 502, incorporated many marine-derived features. Chrysler's 446-pack used similar forged internals. Ford's 460 Police Interceptor was basically a marine engine in a Crown Victoria. But wait, there's more. The most interesting application came from an unexpected source: aircraft. In 1964, a small company called D. Howard Corporation was looking for a reliable engine for their agricultural crop dusters. These planes flew low and slow, often in hot, dusty conditions. They needed an engine that could run at full throttle for hours while ingesting dirty air and agricultural chemicals. Sound familiar? And Howard bought 6 401 Marine engines and had them converted for aircraft use. This meant adding a propeller reduction drive, magneto ignition, and FAA-approved accessories. The installation was certified as experimental, allowing farmers to use them for agricultural applications. The first aircraft, a modified Piper Pawnee, flew in March 1965, and where the standard Lycoming 0540 aircraft engine made 260 horsepower and required 100-octane aviation fuel, the Buick made 280 horsepower on regular 87-octane autogas. Fuel cost dropped from 40 cents per gallon to 18 cents. The Buick's massive torque at low RPM meant the plane could carry heavier chemical loads. The overbuilt cooling system handled the heat of low-altitude summer flying. And the FAA was skeptical. They required 1,000 hours of logged operation before considering certification. The Buick completed those hours in 4 months without a single mechanical failure, not one. The Lycoming typically needed top-end work at 500 hours. The Buick's Stellite valve seats and chrome silicon springs were still perfect at 1,000. And the marine heritage showed in other ways. The engine's ability to run at odd angles, designed for boats in rough seas, translated perfectly to agricultural flying's aggressive maneuvering. The dual pickup oil system kept pressure steady during steep turns. The massive oil capacity meant longer intervals between changes. And by 1967, over 200 aircraft were flying with Buick Marine power. The FAA issued a supplemental type certificate for the conversion, making it fully legal. Howard Corporation couldn't convert engines fast enough. They were buying marine engines directly from Buick, 100 at a time. Let me put that in perspective. An engine designed to push boats was now powering hot rods, winning sports car races, and flying airplanes. All because Buick's marine engineers understood something fundamental: build it stronger than it needs to be, cool it better than necessary, and it will outlast everything else. The technical reasons for this success go deep into engineering philosophy. Most engines are designed to meet specific requirements with minimal excess capacity. It's called optimization. Make it as light as possible while still meeting durability targets. Use the minimum material necessary. This makes economic sense for mass production. Anarch and marine engines couldn't follow this philosophy. A failed engine in a car means calling a tow truck. A failed engine in a boat could mean death. The Coast Guard recorded 347 boat engine failures, resulting in emergencies in 1952 alone. 43 resulted in fatalities. When Buick entered the marine market, they understood this responsibility. Every component was designed with a safety factor of at least 2, often 3. The crankshaft is a perfect example. The automotive crank was designed to handle 350 pound-feet of torque with a safety factor of 1.5, meaning it could theoretically handle 525 pound-feet before failure. The marine crank was designed for the same 350 pound-feet, but with a safety factor of 3.0. It could handle 1,050 pound-feet. When hot rodders added superchargers and made 700 pound-feet, the marine crank was still operating within its design limits. Never the cooling system followed similar logic. The automotive system could dissipate 80,000 BTUs per hour, sufficient for normal operation with a 20% safety margin. The marine system could dissipate 220,000 BTUs per hour, nearly 3 times the capacity. When racers ran sustained high RPM, generating 150,000 BTUs, the marine system wasn't even stressed. This overbuilding had an unexpected benefit: consistency. A traditional hot rod engine might make 400 horsepower on its best day, but after heat soak, that might drop to 350, then 325. Then something breaks. The marine engines made less peak power, but maintained it consistently, run after run, hour after hour. That 275 horsepower was there every single time. The metallurgy was another advantage. The chrome silicon valve springs maintained their pressure even at elevated temperatures. Standard carbon steel springs would lose 20% of their pressure when hot. This led to valve float, missed shifts, and eventually valve-to-piston contact. The marine springs lost less than 3% at temperature. Racers could bang the engine off the rev limiter without fear. In engine, the stellite valve seats were practically indestructible. In automotive applications, valve seats typically showed wear at 50,000 miles. The stellite seats in Thompson's dragster showed no measurable wear after 400 passes. That's the equivalent of 100,000 miles of street driving. The hardness of stellite actually increases with temperature up to 800 degrees Celsius. The hotter it got, the tougher it became. But the real story wasn't just the materials. It was the system-level thinking. Every component was designed considering how it affected every other component. The massive oil capacity didn't just provide more lubrication. It meant the oil temperature rose slower, maintaining viscosity longer, providing better film strength, reducing wear on everything it touched. The larger bearing surfaces distributed loads better, reducing peak pressures, allowing the use of softer bearing materials that were more forgiving of contamination. Marine engines often ingested water through the intake. The softer bearings could embed small particles without scoring the crankshaft. A traditional race engine with hard copper-lead bearings would have seized. On this, the low compression ratio that seemed like a disadvantage actually provided huge benefits. Lower peak cylinder pressures meant less stress on head gaskets, rod bolts, and main caps. It allowed the use of lower octane fuel without detonation. It reduced the temperature of combustion, decreasing thermal stress on valves and pistons. When combined with forced induction, it allowed boost levels that would have destroyed a high-compression engine. When modern engine builders still study these marine Buicks. The philosophy of overbuilding for durability over peak performance has influenced everything from diesel truck engines to Formula One power units. The current Mercedes F1 engine runs a compression ratio of just 8.1, allowing massive turbo boost while maintaining reliability. Sound familiar? The influence extended to other manufacturers. Chevrolet created the Mark IV Big Block with marine applications in mind from the start. Ford developed the 460 with similar overbuilding. Chrysler's 440 industrial engine borrowed heavily from marine design principles. The entire industry learned from Buick's approach. And today, surviving Buick marine engines are highly prized. A complete 401 marine engine in good condition sells for $15,000 or more. That's triple what a comparable automotive engine brings. Collectors understand what racers learned 60 years ago. These engines are nearly indestructible. And several still compete in vintage racing. Tom Malloy's 1932 Ford Roadster runs the same 364 marine engine installed in 1961. It's never been rebuilt, just maintained. After 60 years and thousands of passes, it still makes within 5% of its original power. The compression is still even across all cylinders. The oil pressure is still 70 psi. The boat engine that was supposed to be a joke became a legend. Nenditian, the story of Buick's marine engines, teaches us something fundamental about engineering. Sometimes the best solution isn't the most sophisticated or the most powerful. Sometimes it's the most overbuilt, the most understressed, the most reliable. In a world obsessed with peak numbers, the marine Buick proved that consistency beats capability, that durability trumps dyno sheets, that an engine built to push boats could embarrass purpose-built race engines simply by refusing to brake. Then think about modern automotive engineering. Everything is optimized to the limit. Engines make incredible specific output, but require premium fuel and perfect maintenance. They're designed to last the warranty period with minimal excess. What would happen if someone took the Buick Marine philosophy today, built an engine with triple the cooling capacity needed, forged internals that could handle twice the design power, valve springs that would last 1,000,000 cycles? It would be heavy. It would be expensive. It wouldn't win any efficiency awards. But it would run forever. And in certain applications, forever is more valuable than horsepower. That's the lesson of the boat engine that conquered hot rodding. Build it stronger than necessary. Cool it better than required. Use materials that exceed requirements. The result won't be optimal, but it will be legendary. Titans, the last Buick Marine engine, rolled off the line in 1966. Emissions regulations and the move to thin wall casting ended the era of overbuilt boat anchors. But their influence lives on in every diesel pickup that runs 500,000 miles, in every industrial engine that operates 24/7, in every aircraft engine that values reliability over power-to-weight ratio. The Buick engineers who created these marine engines probably never imagined their creations would become hot rod heroes. They were just trying to build boat engines that wouldn't leave customers stranded. But in doing so, they created something that transcended its original purpose, an engine that proves sometimes the best racing modification is no modification at all. Just massive overengineering from the start. Next time you see a classic hot rod, ask the owner what's under the hood. If they smile and say, Buick Nailhead, Marine version, you'll know you're looking at one of the most unlikely success stories in automotive history. An engine designed to push boats that ended up pushing the boundaries of what hot rodders thought possible. all because a group of engineers in 1953 decided to build something that simply wouldn't break. What's the most overbuilt engine you've encountered? Let me know in the comments below. And if you enjoyed this deep dive into the boat engine that embarrassed every hot rod, hit that subscribe button for more stories of unlikely engineering heroes. Until then, keep those engines running, whether they're pushing cars, boats, or airplanes.